So 3.3 characteristics of polynomial functions in factored form. What we're going to do today is we are going to specifically talk about families of curves. Okay, so this is the day 2. A family of curves is a set of curves whose equations are of the same form, but different values change the shape. Okay, so if we recall that the coefficient a, remember this is a vertical stretch or vertical compression by a factor of a. Okay, so we're specifically going to be talking about this a value and what it does to these equations. Okay, so an example is consider the quadratic function f at x equals x minus 2x minus 4. So clearly this has the zeros of x equals 2 and x equals 4. Okay, so I'm going to reference this graph here. As we can see, 2 is here, 4 is here, those are the zeros. Now, I need to point out that this equation here is not the only equation, so the only quadratic function that has these zeros. There's actually infinitely many quadratic formulas or functions that have these zeros, and what actually ends up happening is this changes. So in the initial one, the a value is actually 1. It just wasn't identified. Now that we have the a value, we can decide whether a is positive or if a is negative, right? And we know that from opening up or opening down. And then whether a is greater than 1 or between 1 and 0. Like the actual absolute value of a, so like the number portion. And what's going to happen is every single time we change a, we're going to be changing the graph. So this is the graph where a equals 2. As you can see, it's a little bit skinnier than the original graph because it's vertically stretched. This is the graph just reflected in the x-axis, so it opens down. So same graph. And then this is the graph both reflected in the x-axis, and this is vertical compression by a factor of 1/2, right? 0.5 is 1/2, and we can see that this is wider. So we can say wider, we can say this is, I don't know, skinnier. Okay, so in general, polynomial functions that have the same zeros and are like simply vertical stretches or compressions of one another belong to the same family. And they have equations in the form y equals a f at x. So you'll take whatever equation it is and you're going to assign some a to it, and those a's are going to be different. Those are all part of one family. Okay. And as a recall, we write each zero in a bracket. For example, with 2 x-intercepts, we would have 2 brackets here. We just call x minus s, x minus t, so the zeros would be s and t. That would be quadratic. Now, cubic is going to have 3 zeros. We're going to have x minus r, x minus s, and x minus t. Okay, 3 zeros. And that pattern continues for any polynomial of degree n. So you can have quartic, and you'd have another bracket. You can have 5-term polynomial, another bracket, 6-term polynomial, another bracket, and so on. So example 1, determine the equation of a cubic function. So cubic, you're already thinking there's 3 x-intercepts, or at maximum 3 x-intercepts. Okay, and it has the zeros of these. Okay, and then the function has a y-intercept of 6. So to start, we can do f at x equals a, x minus r, x minus s, x minus t. Now, these 3 numbers are the actual roots. I'm going to go ahead and sub these straight in for r, s, and then the t I'm going to actually do at the side of the page. I'm going to explain that one. Okay, so we have x minus negative 2, x minus 3, and for a root that's in this form, like the form of a fraction, I want to actually go over this. So In factored form, if you were to be given a polynomial and you were to factor it, you would never actually get a fraction in this position, like where the t is. What you would get is, like for this one, you'll see we're going to get 5x, I think it's minus 2. But I have to actually do the calculation to solve. So what we would be thinking is x minus t, and the t being 2 over 5. And then what we do is we would set it equal, let's go back, let's do it this way, x equals 2 over 5. We can say x equals 2 over 5 because that's actually the x-intercept, like straight from the question. Now, I would cross multiply the 5 up, and we would get 5x equals 2. And then I would bring the 2 over, and I would get 5x minus 2 equals 0. Well, this here would actually be the last factor, 5x minus 2, because when we have the factors and we branch them off, right, with those arrows, what ends up happening is we would set that equal to 0. So now we're just doing it backwards. And then now these are nice integer values. So as a simplified form, and I'm just going to simplify basically these two negative signs, we get x plus 2, x minus 3, 5x minus 2. Now, if you get up to here, you're going to get probably 1 mark, okay? But when we say there's a y-intercept of 6, this is actually an ordered pair. So y-intercept of 6 is 0, 6. Now, take this number, or this coordinate, 0, 6, and what we do is we sub it in. Now we have every single value, and then we solve for a. Okay, so this would be another mark. We get 6 equals a, bracket 2, negative 3, and that's negative 2. So 6 equals 2 times 3 is 6, times 2 is 12, and it's going to be, so you can write it as 6 equals a12 or 6 equals 12a, which is nicer. Divide both sides by 12, I get a equals 1 over 2. So a equals a half. Okay, you get a mark for that. Then if we wrote the equation, is that what it asks for? Determine the equation. So in order to determine the actual equation, you have to come over here and say, therefore, f at x equals 1/2 x plus 2, x minus 3, 5x minus 2. Determine the equation of the following function. Okay, so this time we have a graph, so we actually have to determine the x-intercepts. So we have an x-intercept here at negative 2, and this is going to be, so x-intercepts, let's just make a list, x-intercepts at negative 2, and this is going to be order 2 because it comes up and it pops back down. Okay, because that's a maximum value. Then we have an x-intercept at negative 1, and that's going to be order 1 because it goes directly through. And then we have another x-intercept at 1, and that's going to be order 1. So to start our equation, we can write f at x equals, don't forget this a value. That's the whole purpose of this entire lesson. Okay, a, we're looking at families of curves. We're looking at the same x-intercepts, just like a different stretch on it. Okay, so we have x plus 2, and that's going to be order 2. We're going to have x plus 1, and then we're going to have x minus 1. Right, all of these x-intercepts, we're going to change the sign when we put them into the equation because there are built-in negative signs in the equation. Okay. Now, what we have to do is we have to take a look on the graph for a specific y-intercept, or sorry, a specific point. I'm going to choose the y-intercept because it's nice and clear. So 0, 2. So again, we're going to sub in 0 for the x's and then 2 for the y, or instead of saying y, we should really say f at x. And then we're going to solve for the a value. So I'm going to go ahead and sub in 0, 2. So we have 2 equals a, and that's what we're looking for. 0 plus 2 squared, 0 plus 1, and 0 minus 1. So I'm going to bring down that 2, write the a. So 0 plus 2 is 2, and we want to square that. 0 plus 1 is 1, and 0 minus 1 is negative 1. So in the next line, I'm going to do, well, what's 2 squared? It's 4. And then 1 times negative 1 is negative 1. So I get negative 4a on this side. See how I just flipped these? So I multiplied 4 times negative 1. I get negative 4. And then I put the a there. Okay. Divide both sides by negative 4, and I get negative 1/2. So we can say, therefore, f at x equals negative 1/2 x plus 2 squared, x plus 1, x minus 1.